All right. So thank you all for coming. And I want to talk about, like the title says, a primal-dual perspective. And what I want you to think about is this sort of primal-dual interaction that is very common in verification algorithms between proofs and counterexamples, where you have some sort of procedure that automatically searches for a proof and a counterexample. And those two searches are not just in parallel, they also guide each other. And you can even say that it happens when, when a human thinks of finding a bug in a program or proving a theorem, we kind of simultaneously think of proofs and counterexamples, and those two searches guide each other. And there are some nice examples of verification or automated reasoning algorithms where this occurs, but this is sort of informal. And of course, the classic example of this in computer science is linear programming duality and duality from linear optimization. And there are a couple of recent papers from POPL'22 and POPL'23 that had primal-dual algorithms which had a more formal explicit duality. And those kind of motivated and inspired this work where we're trying to ask, is there a way to capture formally this primal-dual interaction that is common in many verification algorithms? And hopefully this new insight can lead to new insight, this new perspective can lead to new insight on existing algorithms and also maybe to some ideas on designing new algorithms. And indeed, what we were able to come up with is a Lagrangian-based framework, and I'll explain what that is on the next slide, where it is inspired by linear programming duality, and it is able to capture many common algorithms from verification and automated reasoning. And it kind of reveals some interesting comparisons between existing algorithms. And another contribution that we have in the paper is a new algorithm for solving quantified fixed point logic whose design was assisted by this framework. But in the talk, I'm mostly going to focus on the new framework and the perspective that it offers. All right, so we take some inspiration from linear programming and linear optimization, where it's very typical to define what's known as a Lagrangian, which is a function from two sets to R. And it's common to define these two problems, I think the primal optimization problem and the dual optimization problem, where you see x and lambda here, and x is trying to minimize the Lagrangian, and lambda is trying to maximize it. And in the linear programming setting, it doesn't matter which order you take the inf sup or sup inf, and that's what's known as strong duality. Now, to apply these ideas to program verification, we generalize from the setting of just Rn, and we let x and y be general sets, and z be a totally ordered complete lattice. And in this case, it may not hold. Strong duality may not hold. This equality might not hold. But weak duality, which is an inequality here, always holds. And this is a very classic result. It's also known as the minimax theorem, and you can easily convince yourselves of that. All right, so this is pretty abstract. Now let's see how we're going to apply it to program verification. The setting that we're going to define is usually where x is the space of possible and maybe partial counterexamples, and y is going to be the space of proofs. And we're going to define our Lagrangian to be, let's say, -1. So a Lagrangian of a certain x and a certain y, a certain counterexample and a certain proof is going to be -1 if the counterexample shows that the proof isn't valid. It's going to be 1 otherwise. And then we're going to derive sort of a two-player game from this Lagrangian, where the x player tries to minimize the Lagrangian by finding a counterexample that rules out the existing proof. And then the y player tries to maximize the Lagrangian by trying to find a proof that rules out the existing counterexample. So this kind of leads to a pretty straightforward procedure that I'll present with an example. So let's say that this is our Lagrangian. And so we're going to start at some arbitrary point. Let's say we start at this point over here. And then we're going to enter into a loop. And at every step, we're going to let both players take turns. So the x player in this case is going to ask, can we change the value of x to make the Lagrangian negative? And if the answer is no, we're going to declare that the y player wins and return the current value of y. But in this case, of course, we can move here. So we're going to update x to a place where the Lagrangian is negative. And now we're going to let the y player take a turn and ask, can we change y to make the Lagrangian positive? If not, the x player wins and we return the current value of x. But in our case, we're going to update y and to a place where the Lagrangian is positive here. And we're going to let this continue again and again. So the x player could move from here to here. And now the y player can move to here. But in this case, the x player cannot make the Lagrangian negative. So the y player wins, and we return. So this was a very simple example. But what happens if the Lagrangian looks a little different? Let's say it looks like this. So now we might start over here, and then go here, and then go here, and then go here. And now the y player can take us back here. And we're just going to enter into this kind of live log situation where we continuously circle these 4 points, but we're not exploring any new area of the search space for proofs or counterexamples. So how do you get around this? The way to get around this, and this is what verification algorithms typically do, is that they use monotonicity. So if x and y, which before were just arbitrary sets, if they have a lattice structure, and it's enough that one of them has a lattice structure, such that the Lagrangian is either monotone on y or anti-monotone on x, so x is trying to decrease the Lagrangian and y is trying to increase it, then we can ensure progress. And the idea is very simple. We just take the same algorithm from before, and we replace this update by monotonic update. So where we, for example, take the join of the current solution with the new value that shows why the other player doesn't win. And for this modified algorithm, we can prove its partial correctness, its progress under the assumption of monotonicity. And this also can give us termination by stratification, where this is also a common idea, where if you systematically explore either proofs or counterexamples in some order, then you can guarantee termination in case a counterexample or a proof exists. All right, so now the real beauty of this simple algorithm is that we can now start to instantiate it with different Lagrangians and see that we get different existing algorithms from automated reasoning and program verification. So the first example we're going to look at is counterexample guided abstraction refinement, or CGAR. And the idea here is that we have a transition system and we want to prove safety. But the transition system might be very large or maybe infinite state space. And we're going to have some finite set of predicates. And we're going to use it to partition the state space of the transition system into a finite set of equivalence classes according to the valuations on these predicates. And then this is going to induce an abstract transition system, which is finite and possibly small. And we're going to check safety of that transition system. If that's safe, then we can terminate and deduce that the original transition system is safe. And otherwise, we're going to refine our abstraction. So the way this looks like is we might discover an abstract counterexample where we start at an initial state and we make a transition, and then we make another transition, but not exactly from the same state, but from another state that is just equivalent up to this abstraction. And we continue this process all the way to a bed state. And then if we discover this, we just refine our abstraction by adding a new predicate that would break the equivalence between some of these states. So how are we going to get this algorithm as an instance of our Lagrangian-based framework? We're going to let x be sequences of states and y be finite sets of predicates ordered by inclusion. And then we're going to define our Lagrangian to be, so the Lagrangian takes a sequence of states and a set of predicates. And it's going to be -1 if this sequence of states is an abstract counterexample to the abstraction given by this finite set, and 1 otherwise. So now let's try to see what this game would look like. Let's say that we start with some set of predicates, and we let the x player play to minimize the Lagrangian. So what it's going to do, it's going to find an abstract counterexample like this. And now we're going to let the y player play. So the y player wants to make the Lagrangian y. It's going to add to A, because we're going to update A monotonically. It's going to add to A some predicate that would make this condition false, such that it's no longer a valid abstract counterexample for this abstraction. All right. So now let's look at another example, ice learning. So in ice learning, it's also in the setting of safety verification of a transition system. The basic procedure is that we have some finite set of states which are positive, some finite set of states which are negative, and there are going to be initial and bad states, and some finite set of transitions. And we're going to try to find a predicate that is inductive, but just for these constraints, for this finite set of constraints. Let's say we find this predicate. And then we're going to ask ourselves, is this predicate a good inductive invariant for the whole system? And if it is, we are done. And if not, we might refine our finite subset of the transition system by adding a new transition. All right, so this is ice learning. And let's see how we can obtain that with a Lagrangian. So now we're going to let X be the cross product of three finite sets of states, transitions, and initial state transitions and bad states, ordered by the generalization of a subset here. And Y is just going to be our set of predicates. And we're going to define the Lagrangian as follows. Given some sets S plus, S arrow, and S minus, it's going to be 1 if P is a valid inductive invariant for these constraints, and -1 otherwise. So now let's see what this two-player game looks like, right? Let's say we're going to start from some sets of states and initial bed and transitions. So now the Y player plays, and as they maximize the Lagrangian, they're going to find a predicate that is an inductive invariant for this. And now we let the X player play, and the X player, if possible, is going to add a new, let's say, transition to here that shows why this predicate is not a valid inductive invariant. All right, how are we doing on time? All right. So one interesting comparison that these kinds of lets us draw, it both kind of shows the common structure of these algorithms, and it lets us ask what side do they make progress on. And we see that CIGAR makes progress by accumulating predicate on the side of proofs, and ice learning makes progress by accumulating counterexamples on the side, on the side of counterexamples. And I won't have time to go into the details of other examples, but in the paper, we have several more interesting examples of algorithms which we are able to derive from this Lagrangian-based framework. And I will note some interesting properties of them. So for Primal-Dual Houdini, it's a recent algorithm that is explicitly Primal-Dual. And what's interesting there is that it makes progress in a symmetric way on both sides, both on proofs and counterexamples. And also the properties that we have that we derive from the Lagrangian framework, like progress, their proofs are pretty non-trivial for Primal-Dual Houdini. But when you formalize it in the Lagrangian framework, what that translates into is that proving that the Lagrangian is well-defined somehow becomes non-trivial and has to capture the essence of that proof. So there's something interesting going on there, and I encourage you to see the paper for more details. A couple of more things I want to mention here. So we don't have to, this doesn't only apply to safety proofs, it also applies to algorithms for termination. And for termination, we kind of see that classic ideas like disjunctive rankings that let you kind of make use of multiple ranking functions can be seen as a way to make progress on the side of proofs for termination verification. Another interesting observation is that this the algorithm for solving quantified formulas by strategy skeleton kind of reveals that strategy skeletons are a way to make progress for kind of quantifier instantiation in the case of quantified logic. And the last row here is a new algorithm that we derive in this paper, and it kind of, using this perspective, it kind of combines strategy skeletons and disjunctive rankings to get an algorithm for validity of a combination of fixed point logic and quantifiers. So you can imagine how the disjunctive rankings are related to the fixed point logic and the strategy skeletons are related to the handling of quantifiers. All right, another point that I want to highlight that is kind of a part of this perspective is weak duality versus strong duality. So remember that we have a space of possible counterexamples and proofs, and in general, our Lagrangian says whether the proof or the counterexamples wins. When should we expect strong duality to hold? Well, the answer is that it's going to hold if there is either a valid proof or a valid counterexample. And this would hold in finite state cases or in idealized versions. Maybe let's ask the opposite question. When would it not hold? It might not hold if, let's say, the system is safe, but our language of invariance is not expressive enough to express a safety invariant. Or the system is terminating, but our language for expressing ranking functions is not expressive enough for the right ranking. And this is, you consider this is kind of analogous to relative completeness from horologics. All right, so let me conclude. Our main contribution is this general framework based on Lagrangians that captures many existing algorithms and kind of sheds new light on those existing algorithms, and it can also lead to new algorithms. There are many more details in the paper. I want to highlight a couple. One is this new formulation of Primal-Dual Houdini, and the other is this new algorithm that we designed based on these insights. And really what I want you to take away from this talk is a call for action, right? I want you to look at this and take your algorithm or the algorithm that you're working on and ask yourselves, can it be formalized using a Lagrangian as we've discussed? And there can be two answers here. Both are great, right? If yes, that's wonderful. You maybe get some new insight and relate your algorithm to existing algorithms. And if no, maybe that's even better, because if you think that your algorithm has this primal-dual interaction, but it doesn't fit this framework, maybe there is an extension of this framework that is waiting to be discovered. So that's all I had. Thank you, and I'm happy to take questions.
Thank you. Hi, great talk. Tom Ball at Microsoft Research. So if I'm doing abstract interpretation and narrowing and widening, and how does that intersect? Like, what can I tell? Can you give me some hints about, like, because, yeah, that's the question.
That's a great question. So I think we are also asking ourselves that, and I don't have a very good answer. I think you had the right intuition. It's the same that we have, that somehow that's the standard fixed point computation of abstract interpretation. That is not a primal dual, but where the primal dual interaction might come in is exactly in the widening and narrowing. And yeah, I guess answer is welcomed.
This was a very beautiful spin on the duality, and congratulations. So my question was regarding the convexity of the Lagrangian. So I think you've primarily worked on the convex setting. What happens if the Lagrangian is non-convex? Will you still be able to find either a counterexample or a proof?
So that's a very interesting question. I guess convexity plays a big role when the Lagrangian is over real vector spaces. For our Lagrangians, which are kind of over sets of predicates or sets of states, we haven't really defined the notion of convexity. And it would be very interesting to see what might be an analog of convexity in this setting. Yeah, I think it's a great question.
Yeah. Oh, thank you.
Thank you.